Potential difference is just the technical term for voltage. And to try and really understand what voltage or potential difference is telling us, it's useful if we start with an analogy to what we know about gravitational potential energy. So for example, if I move an object to a greater height, I needed to do some work on it. And when I do that work on it, I end up increasing its potential energy by exactly the same amount of the work that I've done. Now think about that in terms of a positive charge. Instead of an object moving to a higher height, imagine that I take a positive charge, or some positively charged object, and I try and move it away from a negatively charged surface. Well, because those are going to attract each other, I need to do some work to pull them apart, to separate them. And so as I pull them apart and separate them, I've once again increased the potential energy of that positive charge. It's a similar idea to what's happening inside of some appliance that's using electrical energy. So let's take a stove, for example. The electrons in the current are passing through a load. And the load is just something that's using up the electrical energy. So in this case, that would be like the metal heating element of the stovetop. And that has its own electric field. The electrons then are moving to a spot of lower potential. And as they do that, the reason why their potential is lower later on is because they're giving up some of their energy to the surrounding atoms. And in this case, that's what's causing the heating element to actually heat up, and the stove heats up. So if we looked at two spots along this circuit, and first looked, for example, at when the electrons are entering that heating element, and we'll call that point A, and then we look again at what the electrons are doing at a point just after they exit that load or that heating element. We'll call that point B. There's going to be some difference in the potential energy between those two spots. And if we measure this, we call it the voltage, and measure it in volts with a V. But technically we do call this potential difference and not potential energy difference, because the actual difference in potential energy, well, that would actually be the work that's being done. Remember, a difference in energy is just the same as work. And the actual difference in energy is going to depend on how much actual charge is flowing through the load. With voltage, though, or potential difference, we want it to be a number that can represent essentially how much push the circuit would be giving to each individual coulomb of charge, and not necessarily how much of an energy difference we would see for the total amount of charge through the circuit. So in order to calculate voltage, or what we call potential difference, we take the difference in potential energy, which is really the work that needs to be done to move a charge, which we'll call Q, from point A to point B. So if we know that work value, if we just take the work and then we divide by how much charge that work is being done to, we get this value of potential difference, which again doesn't tell us necessarily the difference in energy, because energy is going to relate to how much charge actually flows through the circuit. But it's telling us more about how much of a push these electrodes in the circuit are going to give to each coulomb of charge that goes through it. So what we're saying is that 1 volt is actually 1 joule per coulomb, because we're taking something in joules and dividing by something in coulombs. So what that really means, if we think of an everyday example, like a 9-volt battery, you've probably never really thought about what a 9-volt battery really means. What that's telling you is that it's doing 9 joules of work on each coulomb of charge that flows through it. And if it's something like a battery that is a source of energy, that's doing positive work. It's increasing or adding 9 joules of energy to each coulomb of charge that flows through it. If it was something like a load, like our stovetop that we mentioned before, that would actually be doing negative work. It would be decreasing the energy by 9 joules for each coulomb of charge that flows through it. That's what volts means. It's joules per coulomb, the number of joules of energy that are either given from a source or taken away by a load for each coulomb of charge that passes through that source or that load. So if we want to find the voltage and we know how much work is being done and how much charge that work is being done on, we could figure out the voltage that way. But we could also rearrange that formula in a couple different ways. For example, we could just simply rearrange it and say that work is equal to the charge multiplied by the voltage, if we happen to know the charge and the voltage. But remember, work is really just some amount of energy. So in a lot of cases, you may also see this written as E, or energy, is equal to the charge multiplied by the voltage. In our everyday applications, though, this equation isn't always that useful because in a lot of situations, we don't actually know how much charge a certain appliance requires. But often there's other ways, maybe through a user manual or something like that, that we can figure out how much current a certain appliance might use. And remember, current has a strong connection to charge. In fact, current is just charge divided by time. Or in other words, if we wanted to find the charge, we could take our current and multiply by the time. So if we take this value and substitute it in place of charge and do just a little bit of mathematical rearranging, we arrive at an overall formula that says that E is equal to VI delta T. And all the same units that we're using are the same as the ones we previously used. So what that's telling you is that's the amount of electrical energy that would be lost, for example, by a certain current that we'll just call I, through a potential difference of V, over a certain interval of time that goes by, as the energy flows through a load. Now, if this was a source that we were talking about, instead of being energy lost, it would be energy gained, or supplied by something like a battery or a wall outlet. And if we just do a quick unit analysis, we can see that we still will produce the correct units. Because on the left side, we know that we're getting a value of energy. So we need everything from our right side to end up as joules. So if we look at the right side now, we're taking a voltage, which we just said is measured in volts. But specifically, a volt is really a joule per coulomb. So I'm going to write it that way. Then we multiply by current. And current, once again, is measured in amps. But an amp is really a coulomb per second. It's how many coulombs of charge pass a certain point for each second that goes by. And then we just multiply by time, which just like we've always kept with time, we'll keep in seconds. So when that occurs, you can see that the coulombs from the bottom of the voltage unit get canceled out by coulombs from the top of the amperes unit. The seconds from the bottom of the amperes unit gets canceled out by the seconds that we're multiplying by for time. And so the only unit that we actually have left is, in fact, joules. And so once again, this would be a formula that we could use if we know the voltage that something is being supplied, the current that is passing through it, and we also know the time that we are using that thing for, whether it's a load that's going to use up some of the energy, or if it's a source that's going to supply us with some of the energy. So that gives us a few different equations that we can use depending on the situation that we're presented. And so here's a couple simple situations that you might be able to solve using some of these ideas. For example, if we know that a 12-volt car battery is supplying 1.0 times 10 to the 3, or 1,000 coulombs of charge to start a car, let's figure out how much energy is actually being used along the way. So in this case, we're told the voltage is 12 volts. 12 coulombs per second, remember, is what that means. Or sorry, 12 joules per coulomb, I should say. And we also know the charge is 1.0 times 10 to the 3 coulombs. It's another way of saying 1,000 coulombs. And we are looking for energy in this case, which should be in joules in our final answer. Well, as we just saw, we can find energy, which in other words we could think of as work. It's just some change in energy, in this case a change in electrical energy. That energy value is going to be found by doing our charge multiplied by our voltage. So we take 1.0 times 10 to the 3, or 1,000 coulombs. We multiply by 12 volts, which I'm going to just write as joules per coulomb, just so that I can make a little reminder of what's going to happen with our units. When we multiply the coulombs by something that has coulombs on the bottom of the unit, the coulombs just cancel out. And so what we're left with is something in joules. And so essentially we're just multiplying 1,000 times 12, so we get 12,000 joules of energy being used. As always, we want to finish this off with a therefore statement. I'm going to take up the final one in class, but that's of course going to use a bit different formula than the one I just used. In that case, that would be where you know the current, you know how long you're going to run that current for, and in this case we also know how much energy is being supplied, and you can actually use that to work backwards to figure out the voltage of the kettle. So try that one on your own. As I said, we'll go through it in more detail in class, and I can answer any questions you might have about where voltage really comes from in more detail when we take it up.